Welcome to our second online meetup. We have a wonderful speaker today, Andrew Dunning from Portland State. And our panelists today are professional geologist and Professor Sheila Alfson, who is our current president of the Geological Society, now in her second year of being president, or Sheila, maybe it's your third altogether.
It's my third altogether.
It's your third. And Carol Miles is our moderator, also board member. I want to welcome specifically folks that we have from Portland State, from the Geology department there, also from our sister clubs, Central Oregon Geosciences Society out in Bend, Oregon Agate and Mineral, and some of our other friends from the GEM clubs, Tualatin and Clackamas, also people of color outdoors. So I want to welcome the first timers first, because we have, I think about half of the people here are first timers. So I want to tell you a little bit about GSoC. We are the oldest collaboration of amateurs and professional geologists in the Pacific Northwest. We're a membership organization, but our sort of penumbra of membership has expanded in recent years, and no more so than just now with everyone going online. So you don't have to be a member to come on some of our local field trips. You can ask questions in our Facebook group. You can come to these meetups without being a member. Our main concern as an educational organization is to make sure that whatever questions you come to about geology here, we help you find sort of the next step. And whether that's coming to the meetups or going on a field trip or just finding another organization like our gem and mineral friends or our fossil friends, we're all sort of part of this community of the curious, as a friend of mine refers to it as. So to that end, if you feel intimidated by some of the geological conversation or some of the terminology today, remember that there are 10 other people or 20 other people who have the same question and the same uncertainty. We are always accommodating people who are walking in for the first time just with an interest in geology or nature generally, or maybe you took a class in undergraduate years ago, or maybe you were even a geological professional, but you've been in another career. And then we have professionals, we have people in this organization who have been in the organization literally as long as I have been alive. So we want to accommodate that whole range, but especially for those of you who are first timers and have questions about the terminology. We are happy to spend, I mean, I said it's going to go an hour, but happy to spend as much time as, you know, at the end of this. If you have a question about like, what's the next best book to read? What's the best podcast to listen to, or best podcasts? We're happy to have those conversations. Finally, I want to express my appreciation. We lost a really significant member of our community in the past month, Marjorie Bush, who was Secretary of Oregon Agate and Mineral and lately had been working at Rice Museum. She, I think, has done more to bring together these two communities of the gem and mineral folks and the sort of geology buffs. We are actually, I think, literally sister clubs with Oregon Agate and Mineral. We have similar origins, similar founders in the 1930s. And so Marjorie's not here with us today, but we can really appreciate her influence in bringing those two communities together. Sheila, do we have anything we want to talk about in terms of upcoming events? What's been canceled? What's still going on?
What's been canceled is a lot bigger list than what's going on. But we are going to, we are working very hard in the Zoom environment and mastering Zoom enough to bring you some great presentations. So this month we will have, we always meet the second Friday of every month. And it is in the evening. And so our next meeting will be June 12th, and we're going to have Scott Burns, Dr. Burns from PSU, talk on either Iceland or Antarctica. And I haven't gotten the final word on which. Whatever Scott does is going to be fun to listen to. And so that, you know, I'm really pleased that he agreed to do it in the online environment. So it'll be a Zoom presentation, just like the one you're in. And that'll be next Friday. Friday, June 12th. Okay. And the other things, we had a whole lot of field trips planned, and basically everything, at this point, everything's been officially canceled. So everything you see on our website is canceled except for our Colito trip in August. And we're still hoping that we will be able to do it by August. So we're playing that one by ear. The other field trips that we had planned canceled, and if you already paid for some of them, you have your choice of getting refunded or doing it again taking a rain check for next year. Well, we have several field trips. We're going to play everything in a little bit in an impromptu sense. So we have several field trips that we can put together on a short notice. And I really want to get out there this summer. I don't know about you. So if we get restrictions lifted enough, we will put together some kind of quick impromptu ones. I've been leading field trips in the Willamette Valley for 20 years now. And so I could put together any one like that without much preparation. So keep an eye on our website, GSoC.org, and we'll keep you up to date with the latest.
Great. All right. And just to repeat something I might have said before at the top of the hour, which is for our away field trips or overnight field trips, membership is required. But for our local field trips, which are just 1 or 2 or 3 hours, those are open to the general public when they happen. And one of them might be this downtown trip that we've done twice a year now for a decade. We're not going to do it in June, but we might do it in October, or we might just decide, hey, we want to get out there and do it again. My lecture on the downtown tour will be online shortly, and as well as a couple of Sheila's lectures, and our lecture content generally will be on our website, gsoc.org. Well, I want to move over to introducing Andrew. Andrew, I didn't ask you for your formal biography, so I'm going to just wing it. I met Andrew 2 years ago when I was president and I was doing the Hancock field trip. We were out at Hancock Field Station, and we realized we had far more people who were interested in going on the walks around around Hancock. And we heard that Andrew was a PSU geology student, and that not only that, he had been an instructor for OMSI and knew Hancock intimately. So we recruited him then. Since then, I've got to know him through his work on YouTube, and I'm really excited. Andrew, you can add anything else you want to about your bio, but I'm really excited at this lecture, which I think will be about 30 minutes, and then we'll take questions in the chat for Andrew. And again, any questions. What's a rock? What's a desert? Anything is fair game. So Andrew, I'll hand it over to you.
Thank you, Paul. I'm pleased to be here. Well, of course, doing it on the virtual format is different and challenging for us all, but here we are, and it allows me to appear as though I am, in fact, in Death Valley, which is always where I long to be. I think Paul pretty much covered everything important about my biography, geologically related. I do graduate from Portland State with my bachelor's in about 3 weeks now, and then I start grad school in the fall. So I'm just going to jump right into it here. I did my best. Oh, I got a screen share. I did my best to sort of blend more technical information with less technical information. So if there are questions that you have, please put them in the chat, and we will. I might pause 1 or 2 times throughout and answer some of those if Sheila could relay those to me, and I'll definitely take any other questions at the end.
Yeah, I am watching the chat, so feel free to type your questions in, and we'll get to them. Okay.
Excellent. All right. So we're talking about the geology of Death Valley National Park, which is really my favorite place to be. I've been going there since I was literally about 1 year old. I think was my first trip there. I've been, as far as I'm aware, about 25 times. So it's I've grown up in Death Valley. So it's the largest national park in the lower 48 states outside of Alaska, 5,262 square miles. It's 3% of the state of California, about as big as Puerto Rico. It's an enormous area. The valley itself is 140 miles long north to south, about 10 miles wide generally. It's the lowest point in North America, 282 feet below sea level. and it's only about 75 miles from the highest point in the lower 48 states, Mount Whitney, which is 14,505. The world record hottest temperature, 134 degrees Fahrenheit, which is pretty unbelievable, was set in 1913. First made a national monument in 1933 and a national park in 1991. So the overview of the park, it's a very difficult place to summarize in even a half-an-hour presentation. The rock record stretches 1.7 billion years, which is a very long time, and rocks do exist from almost every period in the intervening nearly 2 billion years. The most extensive rocks are limestones and other sedimentary rocks that go back hundreds of millions and billions of years. So we get regional shortening starts to begin about 200 million years ago, which is when limestones stop being deposited. All of that sorts to connects with the formation of the San Andreas and the lateral plate motion, which starts about 20 million years ago. Volcanic complexes in the Miocene and more recent times, full of lakes. There's extensive mining for metals and industrial minerals. Hopefully I will be able to cover all of this. It's a lot of information. Please take notes, and that way you can remember your questions. So I've divided Death Valley into sort of 3 eras. So we can go to deep time, which goes back to even before we can interpret what has happened even before the rocks that we have now existed. We can interpret the formation of North America with rocks found in Death Valley. So I'm calling that deep time. And that goes really all the way up through limestones and granites and all that. And there's the age of volcanoes, which starts about 35 million years ago when you start to get volcanoes and more rocks that we see in fossils start to form and exist. Then more recently, the most recent period, we have lakes and playa. So Death Valley is formed, but we still have all these sequences of earthquakes and lake formations and mineral formations that really make Death Valley what it is today. So this is Marley Miller's fantastic sort of geological overview map, which it gives a good idea, good visual aid to the variety of rocks and the ages of rocks in there in Death Valley. I've made this little map here showing the distribution of Precambrian rocks. That is all rocks older than 542 million years, which is a very long period of time. And so we're going to start there. In the beginning of Death Valley is the Archean era, which goes back to 2 billion years, 2 to 3 billion years is the Archean era, very long time ago. And the rocks, the basement crust of Death Valley predates North America. If you look at this image here from Whitmire and Karlstrom, you can see this is their interpretation of what North America looked like about 1.7 billion years ago. And it doesn't really resemble North America. I mean, we can still see, in the full version of the image, you can see the shapes of Canada and parts of the East Coast starting to look like it. But this whole block here, called the Mojave block, got accreted to what later became North America about 2.5 billion years ago. So the marine environment goes back that far, and some of these sediments that got metamorphosed into the rocks we see today have been interpreted through neodymium analysis, isotopes, to 2.5 billion years. We have 2.5 billion year old sediments that got turned into metamorphic gneiss rock, which is crystallized about 1.7 billion years ago, and marbles and schists and assorted metamorphic rocks. So we have 1 billion years of mud that post-dates that. The earliest fossils even start to show up about this time, with algae and stromatolites and the Pahrump group, which is a limestone and other sedimentary group, which starts out about 1.3 billion years ago. It's such an abstract amount of time that this all covers. It's really nearly impossible to visualize. And this sequence of sedimentary rocks is near continuous all the way up to the Permian time, which is about 250 million years ago. Primarily shallow marine sea at the edge of a deep ocean trough, which is called the Amargosa Alwacogene, one of those weird unpronounceable geological words. And there's some features called mylonites and other faults in the gneisses. This is a mylonite here, which records the history of deformation of the area, which is really important to understanding why Death Valley is so much bigger than a lot of the other valleys around it. But that is exceptionally technical, and I will probably stay away from getting too deep into that. The earliest fossils, stromatolites and algae in the Pahrump group, multicellular organisms, don't really show up until 750 million years ago. So we've already gone through 1 billion years of Death Valley history before we get multicellular organisms. And about this time, we get Snowball Earth, which is a fascinating global event where glaciers covered most of the planet, probably as much down to the tropics. And this is recorded in some limestones called the Kingston Peak Formation and the Noonday Dolomite. This here is called a glacial dropstone. So a glacier scrapes across the continent, and then once an iceberg breaks off, it floats around in the ocean. Any boulders stuck in that ice will fall down to the ocean. And they compress the sediment below them, and then you see sediment draped over the top of it. So it looks like a big rock fell into some mud. And most of the Earth may have been glaciated except near the equator, which is where Death Valley was. It was very tropical up until fairly recently in Earth's history. Death Valley was close to the tropics. This is one that I found in Kingston Peak Formation marble in Mosaic Canyon. So it's about this same time, 750 million, a billion years, around this time when we get some sills, some intrusive volcanics in the southern end of the park, which baked the limestones into talc, which you can see a little bit of it here. It's this whole bottom section. And talc was an important mineral in Death Valley history, and it was mined all the way up until the mid-80s, where there were open strip mines in the middle of a national monument, just taking away talc for a very long time. Some of the cooler features of these older rocks are very well preserved. Many of these sedimentary rocks. Here we have cross beds, and this arrow shows the direction of the ancient water current. This is what happens when sand is moved by flowing water. It causes these formations when sand falls, gets dragged by the water, and it settles out and forms these nice little lines. In the same way, we have these ripples here. This is Precambrian, nearly billion-year-old stuff, and you can see evidence of flowing water. And this is the oldest exposed rock in the park here. This is a nice turtleback. A turtleback is the feature that they're called. They're very technical. Basically, it's an anticline, a fold, where this ancient rock got folded up. And for various reasons, they're very complicated. And it's a big source of research of these turtlebacks. So we have the seas are rising and falling during this whole time. We have a near continuous sequence of marine sedimentary rocks from Precambrian time through the early Pennsylvanian and up into the Permian. The Amargosa-Alwacogen, which I already mentioned, kind of a failed rift is a common interpretation of it. But the basic marine environment is kind of like the east coast of the United States, where it's just sort of a big continental shelf with generally calm waters, warm waters too. Extensive marine fossil assemblage of invertebrates goes through this whole time period, and generally tropical to subtropical conditions. You can see one of these youngest limestones popping up in the Cottonwood Mountains. Really beautiful stuff. Some other limestone pictures. I'm not a sedimentary geologist, but I do love a good limestone. This is Marble Canyon. You can see the dip of these strata, these wonderfully bedded limestones. This algae nodule, this is a clump of algae that got fossilized and turned into a chert, which is basically quartz, microcrystalline quartz. It's about 8 centimeters wide. There's a lot of these. Some of them are perfectly circular. They're so neat. So many cool features in these limestones. And these are, my favorite fossils in the park are these orange corals. This is from the Tin Mountain limestone. This is called a rugose coral. It predates like reef-forming corals like we think of today. This is a very ancient organism, and these ones are about 3 centimeters wide. I have seen them bigger. I've also seen them smaller, and I'm not really sure why they're orange. This whole limestone is kind of this beautiful blue-gray color, but all of the fossils in it are generally this bright orange color, so it's really a really distinctive rock unit in the north end of the park. You see more of these limestones. A lot of them are kind of cliff forming, which is in part because of fast uplift of the mountains and in part because of the slow erosion being in the driest desert in North America. These are early Cambrian ripples. So this is when, if you've heard of the Cambrian explosion, this is sort of when the diversification of animal life really happened in our oceans about 540 million years ago. These are ripples dating from that time. So animals get invented, and we have ripples getting recorded in Death Valley rocks. These are more sort of algae fossils in the Owens Valley group and Lemoyne Canyon. I included this picture, not because I expect you to read all of it, but just to show how continuous and how complex most of these limestones are. I mean, you can see little gaps here and here. That's what these squiggles are. But it's dominantly continuous all the way back from here, 1.3 billion years at the beginning of the Pahrump group, all the way up well into the Cambrian, which is really pretty unique in our country. So some of these limestones have a very, very well-preserved record of sea level rise and fall. And this is not absolute, but they look at the fossils and the sedimentary structures and some of the minerals inside the limestones to determine how deep this limestone would have formed in the ocean. And so that's the Bird Spring Formation, and some of the younger ones, including the Owens Valley group, record sea level changes. And so we call this a carbonate platform when lots of limestones are deposited on a continental shelf. And so we do see this change from sandstones, and then those turn into terrestrial, where we have a called an unconformity, where the continuous rock record ends. It jumps to something else. Above the Permian, which is 250 million years ago, we have a major unconformity as the plates begin to shift, and the Farallon plate starts to subduct under North America, which only, we have a small part of the Farallon plate off our coast in the Juan de Fuca plate. And that's when the granites intrude. So we hit the Mesozoic, which is a very long period of time. This is the age of dinosaurs, and the whole Mesozoic has very few rocks exposed in Death Valley, except for these granites, which were formed deep, deep, deep underground. And you can see their relation to the Sierra Nevada block here, which is almost all granitoid. And so once this Farallon plate subduction, it starts to melt in the mantle, and that produces volcanics and magmas, and all of those magmas rise and started to intrude North America. And the granites in Death Valley are of similar ages and compositions to those of the Sierra Nevada. There's no known surface rocks of dinosaur age in Death Valley, although dinosaur tracks have been found in the Jurassic period and Aztec sandstone south of Death Valley. Margins of plutons are where metal-bearing mineral veins are found. So this is the reason Death Valley was famous for gold and silver mining, and dozens of other metals and minerals are common in Death Valley because of the intrusions of these plutons, these granites. There's some pictures of them. This is the grandstand, which is a lovely granite boulder outcrop in the middle of a perfectly flat lake bed, which is clearly seen from the International Space Station and has been featured in many of their pictures. It weathers sort of this brown color with these large, kind of 3-inch big feldspar crystals in them. So it's really pretty rock. And this is the same rock, but in a different area of that pluton that got rolled down the canyon. You can see someone carved the name of a ghost town in here. It was used as a trail marker many years ago. This is another one. This is the Manly Peak Pluton. They all form these sort of big flat-topped mountains. This is in the south end of the park. This is the north end of the park. These are the south end of the park. And during this time, the crust is shortening because of this, because of the subduction of the Farallon plate going underneath North America. The crust is shortening. Death Valley is getting narrower. And that means rocks have to fold. Rocks have to bend or they break. And you can see this got folded, and then it got folded more, and it got pushed all the way over. So we have these huge thrust faults forming and pushing and folding younger rock over older rock. And in other times, we have older rock getting pushed over younger rock. There's a thrust fault in Death Valley that pushes pre-Cambrian rock over Permian rock. So we go from 800 million years to 200 million years. It's just really neat to see in person. And some of these faults and anticlines and folds have been turned over time. And it's in this time period that Death Valley permanently gets above sea level. And this is that same outcrop viewed from the canyon level. This is in Titus Canyon. The Cottonwood, Grapevine, Amargosa mountains all have several major thrust zones. And the Amargosa Chaos is a jumbled thrust fault where the upper plate, the thrust fault is where the crust gets shortened and it goes over top. And this upper plate is the Amargosa Chaos. It collapsed and sort of turned into this faulted rubble, and it's very interesting and a source of a lot of recent research. So this is what some of these fault zones look like. This is the mega breccia. There's very few of these in the world, but this is, you can see this is a road here. So some of these are 2-3 meters across, and this is what it looks like up close. This is very cool. This limestone got bent and fractured underground when it was deep under pressure, and all these spots got filled in with calcite and quartz, which makes for a really lovely outcrop. And this is a very small fold. This is only about 3 feet across in Lemoyne Canyon, and above it is the Bonanza King Formation, which I'm not recalling exactly right now, but I think this part of the Bonanza King is about 800 million years ago, but this here is 250 million years old. Okay, are there any burning questions in the chat, Sheila?
I was muted. Sorry. No, I don't see any yet, but feel free, folks, to ask. Okay, keep going. You're doing great.
All right, and now we come up to a more recent age in Death Valley, the Tertiary, which is post-dinosaurs. We don't really use the term tertiary anymore, but since it's very difficult to differentiate rocks of this period in Death Valley, a lot of them, even today, even though we use Paleogene and Neogene, we still rope them into tertiary, geologists do. So after 200 million years of mountain building, Death Valley erodes down to a rolling upland savanna. And at this time, the Sierra Nevadas mountains start to rise. And they start to erode and streams start to flow towards Death Valley. And these oldest rocks we see from this period, which is about 38 million years old in the late Eocene period, the transition to lateral plate movement begins to push up the Sierras and pull apart the earliest Death Valley basins. And so this is the Titus Canyon Formation, is sort of the first mammal age rock we see in Death Valley. And this is a titanothere, which is one of the biggest fossil, I think, found in Death Valley. It's the size of a rhinoceros, and we have similar animals in the John Day fossil beds in Oregon. Brontotherum is the genus. And also Mesohippus, which we are famous for in Oregon, is horse fossils, also found in Death Valley. So extension is beginning about this time, 20 million years ago, 15 million years ago. It's very slow, this transition to lateral plate movement, and where we start to have big fault zones starting to form. I know a lot of researchers date the San Andreas fault zone to about 20 million years ago, thereabouts, big range, and this is when the Death Valley faults start to begin. But the beginning, the genesis of these fault zones and the arrival, possibly, depending on who you ask, of the Yellowstone hotspot, could have influenced volcanism in the area. So we have, through central Nevada and eastern California, numbers of huge calderas that had enormous volcanic eruptions that blanketed the landscape in what are called ash flow tufts, which is when an ash cloud sort of collapses and fuses itself onto the ground. This is a big glassy zone of it. There's a lot of glassy ash flows and rhyolite flows in Death Valley and in the Sierra surrounding areas, excuse me. So you get the Furnace Creek Fault Zone and the San Andreas Fault Zone are the most important ones generally in tectonics in California. And they started to form about 20 million years ago. And I talked about those gneisses, the metamorphic rocks. They're cool now. It took them 1 billion years to cool down. They finally dip below 350 degrees Celsius and start to record deformation in a different way. So large calderas and local rhyolite, dacite, and basalt volcanoes start to cover the landscape and really start filling in some of these oldest basins that are forming as a result of the faulting beginning. And that's the Artist Drive Formation and the Funeral Formation are the most extensive of these. We have lots of volcanic rocks in the surrounding mountains in Death Valley. And the earliest stage of Death Valley, really the earliest basins, are a chain of lakes that vary in depth and size. Regional tectonics are rapidly changing at this point, and we get the earliest basins in Death Valley. Fossil animal tracks are valuable fossil record of Death Valley. I was reading a paleontology report as I was preparing for this, and they were, it was written before the park was made a national park. And they were saying that certain fossil localities would be worthy on their own to become national parks as a result of their fossil resources, specifically from this period between 5 and 10 million years ago. Mudstones and conglomerates are sort of filling these basins from flooding from the Sierras, from local mountains that are starting to form really 5 million years to present. And volcanic rocks that filled these lake basins and their ashes and the sediments came off of them are enriched in borax minerals and borates. And borax was mined in Death Valley from 1870 about to 2005 was the last borax mine in Death Valley closing. So some of these formations did not form in basins. This is the Nova Formation. This is a high school age me. Very proud of these bright red fanglomerates. So this is the earliest stage of the Panamint Mountains, which are the biggest mountains in Death Valley. They go to 11,000 feet. When the Panamint Mountains were starting to rise and the valleys were starting to drop, these fanglomerates, this alluvial fan, this is debris flows coming off the mountains and landslides and flash floods and all sorts of stuff like that. This is about 5 million years old. And I was talking about fossil footprints. The most famous place in Death Valley is called Copper Canyon, and that is closed to the public, and I've never been there. However, there are a couple of locations in the park that are poorly documented and not closed to the public. And this is one that a friend of mine located, and it took me 2 years to find, but we did finally find camel footprints. I didn't include a scale in this, but they're about the size of my hand. These are big camel footprints. There's a whole big line of them going up the canyon wall. This is the finest example I've seen with my own eyes of fossil tracks in Death Valley, but it's the, Death Valley has the largest collection of vertebrate track fossils. It was either in the Western Hemisphere or the world. It's a truly exceptional fossil locality. And so to sort of illustrate the complexity of this period in time in Death Valley, this funeral formation, which I mentioned, is the youngest rock in this image. The artist drive is similar aged, but the funeral formation is generally younger than that because of the faulting, which the big fault runs, the Furnace Creek fault runs sort of between the foreground and the background here. This basalt is 5 million years old, but the funeral formation dates as recently as 2 million years. So the faulting has allowed this basin to drop, which is one of the earliest stages of what we see today as Death Valley. And this Artist Drive Formation is deep lake deposits from an even earlier basin that has been altered and is rich in borax minerals. You can see sort of the same thing here. This is in sequence though. This is Funeral Formation conglomerate over deeper water Artist Drive Formation, which alters into these beautiful colors. And there's an 11-year-old me looking at the beautiful hills of the artist palette. Mm. So we enter the age of lakes, which is the most important to modern Death Valley topography and what we see in the park. Here we have a beach. There's not a lot of water in Death Valley today that would produce a beach, but here, several hundred feet above the valley floor, we have a lovely beach sandbar. So why is that? So during the last ice age, during the wetter, cooler climate, allowed glaciers to form in the Sierra Nevada mountains and greater rainfall and cooler climate generally in Death Valley and much of Nevada and California. So these valleys were able to hold huge lakes. Lake Manly in Death Valley was the largest and deepest one in Eastern California. It's 600 feet deep. It stretched 140 miles north to south, 600 feet deep at maximum, dried out about 15,000 years ago. But a smaller, shallower lake persisted until about 2,000 years ago. So there were humans that were inhabited the area. The first humans, the GSoC culture, the Clovis cultures, came into Death Valley about 9,000 years ago. And so they were here to see these huge lakes in Death Valley and definitely survived because of the greater animal life that existed because of these lakes. And it's the drying out of these lakes that produced the extensive salt pans that Death Valley is famous for today, which you can see in my background image. I'm going to jump around a little bit. I wanted to finish the geologic history sort of before I started getting into some other stuff. So the faulting that caused Death Valley is pretty complicated in itself, but also very interesting. It's bounded by major faults, both on one side and on the bottom side. And it's really a textbook example of what's called Horst and Graben topography, much like most of the Great Basin, where you get a mountain and two valleys, where the mountain gets pushed up and the valleys fall down. And some of the evidence of this is a steep fault-controlled mountain front. You can see the bottom of this is vertical because that is the fault trace. And this is all very steep because it uplifted very quickly and erodes very slowly. So here's sort of a general diagram of California and the tectonic environment. You have the San Andreas Fault here, which is called right lateral. So this is going this way. The coast is cruising north. The rest of North America is sort of slowly moving this way to the southwest. Excuse me. Ooh, excuse me. And the San Andreas Fault has this dog leg here, which pushes up on this Mojave block, it's called now, which is a remnant of that ancient Archean crust that I mentioned earlier. And this whole block is rotating, which pushes up, which forms this, the Garlock Fault, which is California's second largest fault, which is left lateral, so it moves opposite of the San Andreas. This is moving this way, and this is moving this way. The rotation of this block pushes the Sierra Nevadas to the north, which drags the whole western half of Death Valley also to the north. You can see here some of the faults in Death Valley. This is the Furnace Creek Fault Zone, which is 160 miles long. This is the Garlock Fault. The Southern Death Valley Fault Zone interlocks with the Garlock Fault Zone and causes this normal fault here, which is downward motion, which accommodates the dropping of the valley, the rising of the Black Mountains. So these major faults, the Garlock and the Furnace Creek and even the Panamint Valley Fault here, are mostly north to south, side to side motion with very little vertical movement. And so it's these other red faults here, which are normal faults, which have downward movement that accommodate the dropping down of the valley. Very, very cool, very interesting stuff. And the dropping down of the valley has allowed, you can even see it here, this is the salt pan, which is 5 miles wide. And the alluvial fans here at the base of the Panamint Mountains, which are uplifting. This is uplifting, this is dropping down. These alluvial fans here that come off the mountains are 5 miles long, thousands of feet high. If I zoom in on the north side, you can see the Furnace Creek Fault Zone and how some of these other mountains are getting stretched apart by with these other basins in between that allows smaller lakes like the Racetrack Playa to form. It's a really, really visible example of pull-apart basins, which is what it's called when two strike-slip side-to-side faults sort of move in a way that stretches the crust. Difficult to explain and visualize, but that's the gist of how it works. So Death Valley, the last earthquake, if you drive through the park today, you can see earthquake scarps. I've drawn this one in black. This is another Marley Miller photo. Her photos are tremendous. And I guess I kind of hid the fault scarp with my fancy line here, but it varies in size from a couple of feet to 10, 20 feet in height. And the best estimate we have is that it's about 1,000 years ago. It could have been about a 7 if it all ruptured, a magnitude 7 earthquake if it all ruptured at once. So it could be a significant seismic hazard. But we know this because of offset alluvial fans. We know how old the lake shores are. Those are datable, so we can find out how much they've been offset since they were formed by earthquakes. So there's maybe 3 to 4 earthquakes on the Furnace Creek Fault Zone, maybe 2 to 3 on this, the Death Valley Fault. But park policy prevents us from doing some of the paleoseismology work, which usually requires lots of digging and heavy equipment to establish the real earthquake hazard and how much it moves. So we estimate that these faults are probably accumulating about 1 to 4 millimeters of strain a year. I know I'm definitely running over time a little bit here, but there's just some cool stuff that I really could not resist tacking on to the end. Death Valley is still a volcanically active place. There's modern volcanism, there's hot springs in parts of the park, and then there's this big old crater in the north end of the park. It's called Yubi-Hibi Crater, which means coyote's basket in the local Tibsha Shoshone dialect. It's a phreatic, a steam explosion that dug out sort of 7 craters in the area and laid tephra and ash and debris across the landscape. And this crater here is 700 feet deep and a half a mile across, a really big hole that got blasted out when magma rose along the Racetrack Valley Fault that uplifts the Panamint Mountains, and encountered groundwater possibly from the local lakes in the area. And when magma hits water, it explodes and digs out big craters like this. And so we know that Death Valley is not done being Death Valley. The Racetrack Playa is sort of a internet famous place where the rocks mysteriously slide across the lake bed. You can see there's a rock here. This is probably about 1 foot high, maybe a 75-pound length of limestone. And it's got this trail behind it going off into the distance. And so you see all sorts of internet conspiracy theories about, it's a magnetic vortex and gravity anomalies and aliens or whatever. But in the truth, this playa is at about 4,000 feet in elevation. And even in Death Valley, they get plenty of snow. I've seen 1 foot of snow on the racetrack, plenty of water in the winter. And this lake contains a lake in many of the winter months. And because it's at high altitude, it freezes. And there's nothing to stop the wind there. So we get these sheets of ice forming on the lake and these high winds that blast down the valley, which mobilize the ice sheets, which do have enough momentum to move and drag big, heavy rocks across a slippery lake surface. And so there's no need for magnetic vortices or gravity anomalies to explain the mysterious moving rocks. And finally, I'm going to finish this off with Devil's Hole, which is really a cool, mysterious feature of Death Valley that a lot of I love. I love Devil's Hole. It's a little tiny square of national park that's isolated in Ash Meadows National Wildlife Refuge in Nevada. There's a lot of hot springs there, warm springs that come up out of the ground. It's a very beautiful place. And there's this natural cave here, which contains 90-degree Fahrenheit water and has the smallest habitat range of any vertebrate on the planet, the Devil's Hole pupfish, which the entire range of it is in this photo. This is I think the water level at this time, this is a National Park Service photo, it's about 60 feet long, maybe 10 feet wide. That's the entire habitat range of the Devil's Hole pupfish. So there's this cave here, obviously, that formed along a fault. No one knows how deep it is. We've been down to 450 feet. No idea how much farther it goes below that. It's pretty wide. It varies, lengthwise, the width is from a couple of feet all the way up to a couple of hundred feet. There's a couple of other rooms along this cave, which exist in this sort of plain. But no one knows how deep it goes, and it's part of this, connects to this vast aquifer, which covers much of southern Nevada and reaches all the way to the Nevada test site, where they did some fun things with nuclear weapons. Oh, I forgot about the sand dunes. The sand dunes are why a lot of people go to Death Valley. The most famous ones, most popular, most visited ones are the Mesquite sand dunes, which are the ones you see all the pictures of on the internet. My favorite ones in the park are the Eureka Dunes. There's 7 fields inside the park. The Eureka Dunes are the tallest in the park, and probably in the nation. They're about 700 feet tall. There's my dad and I for scale right there. This is at the very top. So sand and silt from the alluvial fans and the plains and lake beds pile up against the mountain fronts, creating huge sand dunes. Some of my favorite books, if you're interested, I read these all the time, whether or not I'm giving a presentation. Great information here. Marley Miller's website also has many pictures. Some of my references. I'll open it up to questions now. I know it's a lot of information.
Andrew, that was fantastic. Thank you.
Great. Yeah, thank you.
Thank you for having me.
I know one of my questions is going to be, I know Death Valley is a pull-apart basin, and if you kind of explain that, and can you compare it to any features that we would find here in Portland, which is also a Portland basin, a pull-apart basin?
Yeah, the Portland Basin is a pull-apart basin as well. So is Los Angeles. The Los Angeles Basin is also pull-apart, where you get, even in a compressional environment like in Oregon and that part of the San Andreas where Los Angeles is, just the different rates even that two parallel fault zones will move causes an extensional, a stretching strain on the block of rock, which causes faults to form and basins to drop. This picture is our annual campsite where we've been going for 12 years now. And you can't see it, but actually you can see a little bit of here. This is where the fault is. This is Death Valley. And I'm sitting in a pull-apart basin here, the Furnace Creek Fault Zone, and these mountains are moving, relative to where I'm standing, these mountains are moving that way, and I'm moving this way, which causes this strain here in this alluvial basin to fill up here.
Okay. Do you want me to address the questions that came in on the chat?
Oh, yes, please.
Okay. Let's see. You mentioned, somebody said that they thought that accretion may need to be explained. So do you want to explain it? And I also have an animation that I can show you that explains it very well.
You have an animation? Yes, use the animation.
You want to see the animation? Okay, let's see if I can share.
I can answer another question while you're pulling that up as well.
Well, Andrew, why don't you explain accretion to the best of your ability while Sheila's finding the animation?
Okay.
Especially how, I mean, and I know this is a lot.
Are you going to want to share your screen? Because if I share, I'm going to go over you.
He's just going to talk, I think, Sheila.
Yeah,
Could you explain sort of the transition from accretion to slip faulting?
So say an island, imagine Indonesia on an oceanic plate, which is moving towards North America. North America's, I mean, it's moving, but it's not moving as much as the ocean plate is. So the ocean plate is, because it's heavier and colder and more dense, goes underneath North America. Now, if you've got an island here, it's going to get stuck on North America. And the subduction zone fault is going to have to move because Indonesia doesn't want to move. It gets wedged. It's not dense enough to get subducted down to the mantle, so it stays on the surface. And that's how we have most of Oregon is accreted like that. The continent, the sort of the ancient continents. Here we go. That Death Valley was made of.
You want me to keep? Okay, so just what Andrew was saying here. So we've got an island here, and then we're going to have. Let me start the animation. Okay, we have a subduction zone going on here where two pieces of, these, in this case, they're volcanoes, but just chunks of land. They could be just chunks of land. And then moving across on the plate. And notice that over here, subduction is going on. But these chunks on top of it are too big to go under the other continent, the continental crust, and so it gets pasted onto the side. And that's the process of accretion. That's how continents grow, by other pieces of land moving on, moving plates, and then not being able to subduct and go under, and so they just get cemented to the edge of the continent.
And I know Andrew and I are both from Southern California originally, so really, and Andrew, where are you from again?
From Orange County.
Orange County, and I'm from the San Fernando Valley. So is everything west of the Death Valley in Southern California, is everything west accreted?
I'm not sure. I think it depends where you are. Now that I think about it, it probably mostly is. Even so we do have age equivalent rocks in California that aren't found in Death Valley of that sort of 200 to 200 million, 250 million years to sort of 40 million years. There's a lot of those rocks in California. I believe a lot of those are oceanic, but there are also terrestrial continental rocks that got accreted terrains. So I would say probably everything west of either the San Andreas Fault, if you're down in Anza Borrego, or really south in California, up to the Sierras would probably be mostly accreted terrain.
Yeah, okay. Let's see, we had another question about, let me see. Okay, somebody's asking about paleoseismology. So how does it work? How do you know about ancient earthquakes?
Oh, okay. That really is the $65,000 question. It's complicated. That's a whole geological field in itself. It's, it can be pretty easy if you're in Oregon and you have lots of, say you have an earthquake that ruptures. And an earthquake big enough to cause significant damage really does cause surface rupture generally. There are notable exceptions, but usually there is some sort of surface displacement. So maybe a creek will get aligned differently, or a ridge will get offset laterally. And that leaves what's called an earthquake scarp, or you get sort of a dramatic change in topography. It's flat up here, and then it's flat down here, and all of this is where it moved. And you can age those scarps with a number of different methods, or you can either try and date the scarp of the earthquake, or you can date the offset of an earthquake. I know in Oregon, which is where our PSU advisor, Professor Ashley Stride, has done a lot of work at the Gales Creek Fault. These earthquake scarps get filled in with wood debris and tree detritus. And you can carbon date the tree detritus and find out how long it's been since that scarp collapsed and buried some wood remains. In Death Valley, we date earthquake offsets sort of as a function of time rather than finding individual events. So we can see if there's a beach deposit from Lake Manly, which we know probably happened between 17,000 and 15,000 years ago. There are specific age dates for specific shorelines. That's pretty well understood. And if you look at a 15,000 year shoreline, and it's been offset by 4 meters. We know how much that fault has moved in the last 15,000 years. And using calculations, we can calculate how much it probably moved during each earthquake. And if you're able to do a trench, if you're able to do a cross-section of the fault, you can look much more specifically with much higher detail about the way it moved.
Okay, we have another question about the Garlock Fault, and somebody was asking, were the Sierra Mountains, the Sierras, were they once south of the Garlock Fault?
Let me put up that picture again. That map, Sierras, here it is. So the Sierras have always been right about here. The Garlock Fault, which is this one, formed as a result of the San Andreas Fault. It puts pressure on this block, which is solid. This is solid, you know, multi-billion-year-old crust here underneath the Mojave Desert. And we have more of those old rocks, same type we find in Death Valley, sort of right along here in these mountains, the San Bernardino Mountains. So this block is really solid. It doesn't like to move that much. It mostly acts together. There's a couple of faults and shear zones in there, but mostly it's solid. And the San Andreas Fault pushes against this solid block here, which pushes up on the Sierra Nevadas, which are also solid and do not like to move. So the Sierras have not moved relative to Death Valley too far. There is possibly as much as 60 kilometers of offset along the Furnace Creek Fault zone, but there could be that much along all of these. So the Sierra Nevada arc maybe could have been a few more kilometers south, but it was never south of the San Andreas, and it was never, the Garlock Fault has always been affiliated with it. But does that answer your question? Kind of a circuitous answer.
No, I think it was a good answer. You know, you mentioned that the Garlock Fault is a left lateral strike slip, where the San Andreas is a right lateral strike slip. There was also another question about the earthquake that happened yesterday, and I have kind of an interest. I was watching the news, and the meteorologist on the news was trying to explain it as a strike slip fault, but I thought, gee, they need to know their geology a little bit better.
It was a strike slip fault.
It was a strike slip fault?
Yes,
okay, but most of that area is due to extension, so that would be block faulting.
I had to look at that moment to answer a couple
must have been an oblique fault with a lateral movement as well. Okay.
It was an east-west aligned fault, which corresponds with a couple of mining areas. It's right about here is where it was. Actually, I can pull it up on, I can screen share my Google Earth. And I can show, because I have it all, I have the faults database on my Google Earth. Screen share Google Earth, there we go. No, that's a lot of place marks. It'll take a second to load. I do need my place marks to know where it was. Candelaria. Okay, so there's this left strike slip fault zone right here, which is dominantly strike slip motion, which is bizarre and interesting that it's going this way in the middle of Nevada. Like epicenter was right here, right at the sort of intersection of these normal mountain front faults and this strike slip zone here. Mm-hmm. And I haven't personally seen any, but the word on the street is that there is some surface displacement along Highway 95 here.
Mm-hmm. Yeah, they said that on the news too. Yeah.
Very interesting tectonic environment. And when you see all of the different faults going on here, it's kind of a mess.
Good.
I love it. This is where the Ridgecrest earthquake happened this summer, was right in here, which was also very interesting. Anything else?
can we take any, we can take any other questions anybody has. Make sure and unmute yourself.
The reading list again.
Oh, yes.
You could just put that up one more time, please.
Yeah, yeah, oh yeah, thank you. I missed that one in the comments.
Hey, Andrew.
Yes.
Carol Mills here.
Hello.
Great talk. Thank you very much. I was wondering if you could sort of give an idea of, like, if somebody were to visit the park, where would you recommend they go in terms of being able to see some of the stuff you've talked about, some of your favorite features?
Well, there's a little bit of everything in Death Valley, and because it's so big and so remote, it's impossible to see everything in one trip.
All right, well, that is our hour, so we're going to have Carol stop the recording.